Practice exam for Unit 4. Called fill in the blanks ones here. So make sure for this one you're seeing 2 steps. That's one of the keys. You see a bromine, and you see you added 1 carbon. That's carboxylic acid. So one of the ways make carboxylic acids is with Grignards and CO2. So first you got to make the Grignard though. So you got to turn this carbon-bromine bond, get the magnesium to insert in there. That makes a Grignard. That reacts with CO2. And then you need H plus at the end to actually protonate this. Next one, this is one of the Mountain Carbonell kind of questions. So carboxylic acid is at the bottom. This is the least reactive because it's an acid. So one of the ways to make it more reactive is to turn it into an acid chloride, and that's with SOCl2 and pyridine. This one has a lot. This last one has a lot of possible answers. So H plus is the catalyst, water is the solvent. You make a carboxylic acid. What could you have made it from? You could have made it from an acid chloride. You could have made it from an ester. You could have made it from an anhydride. And it really could be any type of ester. So any of these answers are possible there. Move along to number 2. For this one, really careful reading. Which reagent is most likely to react below, the amine or the alcohol? So we're trying to ask which one's more reactive as the nucleophile. How do I know it's nucleophile? Because it's reacting with an ester. Right? All of these, the carbon of the carbonyl group has been the electrophile. Right? This is the electron deficient carbon. So everything else has been nucleophiles. Which one's more nucleophilic? Actually, the amine is, because it's less electronegative. So it holds its lone pairs less tightly than oxygen. So the amine is the one that's going to react. But first, you have H+, so you have acidic conditions. So you decided on this, hopefully. Acidic conditions, protonate, adds in, right? And I asked you for labeling all the steps. Proton transfer, elimination, and then deprotonate to remake H+, because it's a catalyst. And you make an amide. If you had messed up and picked the OH, that's okay. The way I set this up was you'd still earn all these points. You just would miss those first couple. You wouldn't earn those first couple points. So for number 3, mechanism, label each step, and then also give the missing inorganic product. So inorganic means not carbon. So in this case, you have an acid chloride and you have a carboxylate. Electrophile, nucleophile. Nucleophile has a negative charge. So you just do an addition. And then you have a tetrahedral intermediate. Do I have a good leaving group? You do. Chlorine. So you do elimination. And that gets you the product. And your byproduct you make is Na+, and then Cl-, just sodium chloride. All right, so for number 4, well, you have carboxylic acid and alcohol. This is going to be an intramolecular esterification. You're going to make an ester or a lactone when it's in a ring. Acidic conditions. First step, protonation. All right, protonation. Then you're going to add in proton transfer. Electrons come down to elimination, kick out the water, regenerate the catalyst, H+, and then waters. Because you're going from a carboxylic acid, you're doing a condensation, so you're generating water in this step. And I think on the practice I might have had water here, but I should be just any organic solvent would have been fine. And the reason why this doesn't react is because this alcohol is closer, right? So an intramolecular reaction versus inter. Mechanism of the product here. So I gave you the other byproduct, trying to give you a hint what's going to happen. So first, you have a base, you have pyridine, you have a carboxylic acid. So it's going to be a deprotonation. Then the carboxylate is going to do an SN2. And that's going to give you another ester and this. So, maybe a challenging problem. I didn't give you the product here, but I gave you one of the products, trying to get you try to take a step back and think about what might happen. So number 6, give the mechanism arrows for the reaction below. So this is a classic aldol condensation. All right, so I see the condensation here. I see the base catalyzed. I see a aldehyde and a ketone. And only one of them has alpha hydrogens, right? So only one of them can be deprotonated, right? So I'm going to deprotonate the only one that has alpha hydrogens, make the enolate, so deprotonate. I'm going to add in, then I'm going to protonate, because I have no good leaving groups. So now I have the aldol. And then, because you see here, right, the condensation is going to happen. The OH comes, and we do an E2 elimination. And somebody might ask, well, how does that happen? Why does that happen? You'll notice all of these pi bonds are now conjugated, right? By doing this elimination, you put a pi bond here, and all of these electrons can be in resonance. So now they're all really conjugated. So that's one of the reasons why this happens. Number 7, mechanism for the reaction below. I always put, sometimes I'll say label the steps. I've been trying to always label the steps just to get you thinking about it. This is also aldol condensation. It's a little tougher because now you have 3 carbonyls. You have a lot more going on. So a couple things to think about. You want to find the most acidic CH. So remember, the H is between 2 carbonyls, a 1,3, right? This H can do double resonance, essentially. So that's the most acidic. That's why it's going to be deprotonated there. So that's going to be the nucleophile, and that's going to be the electrophile. Also, you can look at the product, and you can notice here, I kind of drew this squiggly line. Remember, that is the spot where carbon 2 has the C double bond O, and the one between carbon 6 here is actually the nucleophile. So that's like a trick to see where it all happened, right? That's how I knew this was 6 and this was 2. So you do your deprotonation with LDA, a really large, reactive, bulky base. Deprotonation, it adds in, right? I made it ugly, then I made it pretty. A lot of good numbering here. And then we want to deprotonate the LDA, deprotonate the amine, which then can then take away another alpha CH. Notice the CH it takes between the 2 carbonyls, that's the most acidic one, and do another elimination, which makes OH minus and this amine. And again, this happens because I told you it's going to happen, but also this nitrogen, it's pretty reactive, negative charge. So that's what's going to take place. Good numbering is important. Which H is the most acidic? And kind of seeing where this pi bond forms is where things will break. So 6 was the nucleophile, and 2 was the carbon of the carbonyl group. That was the electrophile. All right. Again, mechanism and label each step this time. A little different than the last one. So this one contains an aldehyde and an ester. So you normally know an aldehyde is more reactive than an ester. So the alpha CHs are usually more acidic. But you don't have to worry about it here because if you look closely, this ester, there are no alpha CHs. So you're going to have to deprotonate at carbon 2. So you're going to make an enolate. Notice again the base, right? This ethoxide, 2 carbons, matches the ester here. So this certainly could add in, but it's not going to change this ester. So we're going to deprotonate, make the enolate. We're going to add in, made it kind of looking ugly. Again, we have a tetrahedral intermediate, but now because this is an ester, we actually have a good leaving group, right? So the electron's going to come down and then kick that ethoxide out, which, right, notice is a catalyst. That's another kind of key to remember. You can't stop. You're not done with the reaction until you've remade the catalyst. And there you got your product. All right, some enamine chemistry. So combining a couple different things we've done. So first thing, you have 3 things. We have H+. If you have H+ around, protonate the carbonyl oxygen. Protonate. The amine will add in, right, acidic conditions. Balance your charges. Proton transfer. Elimination. You make the aminium. You do this deprotonation elimination where you make the enamine, right, because we need to regenerate H+. So now we have an enamine. The enamine electrons are going to come down. Pi bonds going there. Little SN2 addition, right? And I actually added another layer to ours. I said I wanted you to actually do have the Br minus floating around. It doesn't need to be the Br minus that does it. It could just fall off. The electrons fall off, and these go there, and you actually regenerate an enamine. Added a little wrinkle. So you had to do that last step before you're all done. Careful numbering, acidic conditions, protonate, basic conditions, add or deprotonate, right? Keep those things in mind. Neutral conditions, no charge, charge, no charge, charge.